We're looking to find the vector equation and parametric equations for a line through a given point in three-dimensional space that's also parallel to this vector 2, -4, 5. Let's recall that in order to find a line in three-dimensional space, we need two things. We need any point that's on the line, and of course we have been given that, and we also need a vector in the direction of the line. And this feels very similar to what we needed for writing the equation of a line in two-dimensional space. When we were writing the equation of a line in 2D, we needed a point and the slope, and here we're needing any point and the direction vector. Basically the same kind of information, a point that puts us onto the line and a piece of information that gives us the direction of the line. So in this case, in three-dimensional space, that would be the direction vector. Of course, the point that we have is 0, 1, -3, and the direction vector that we've been given is 2, -4, 5. And the formula that we're going to be using to determine the vector function for the equation of a line, and here is our notation, it is going to have an input that is a value of the parameter, and the output is going to be a vector that points to a ordered triple that is on the line. So input a value of the parameter, output is a vector. And our vector function formula is going to be an initial position vector, which we're going to get from the initial point that put us on the line, plus a scalar multiple that is the parameter times the direction vector, which we've also been given. So what we're going to do is we're going to turn that initial point into a vector that is a position vector initiating at the origin and terminating at the ordered triple that is the only point that we know is on the line. So this is a vector starting at the origin and terminating at 1, 0, -3. So we've turned that point into a vector, and then of course we have our direction vector given to be 2, -4, 5. So we take these two vectors and use them to create our vector function. So we have 1, 0, -3 plus a scalar multiple of our direction vector, which is 2, -4, 5. And essentially, this can be our final answer, right? We have a vector function now that depends on or has an independent variable that is this parameter t, and is going to be the sum of these two vectors. Now we can rewrite this a little bit. We can write this in a couple different forms. Let's distribute this parameter into the vector. We'll distribute this scalar multiple into my second vector, and we'll end up with 1, 0, -3 plus 2t minus 4t 5t, right? So we have a scalar multiple of our direction vector here. And then we can also go ahead and add these two vectors together to get 1 plus 2t. So we're taking our x components and adding them together. And then if we add the y components together, we're going to get 0 minus 4t, which of course is just -4t. That's my y component. And the z components added together are going to be -3 plus 5t, and that is going to be my z component of my vector function. So here is another way, and actually my preferred way, of writing the vector function here. Now, we've also been asked to find the parametric equations, and the parametric equations for a line can be extracted straight from this vector function. The x parametric equation is the x component taken directly from the vector function. The y parametric equation is the y component taken directly from the vector function, and the z parametric equation is similarly the z component. So we have 3 plus 5t is my z parametric equation. Now we can leave it just like this. This is perfectly fine as an answer to what the parametric equations for this vector function are. We could also use functional notation, and sometimes you'll see x as a function of t, 1 plus 2t, y is a function of t, -4t, and the z parametric equation is also a function of our parameter, -3 plus 5t. So you may also see parametric equations written using that functional notation. So let's check our answer over here on GeoGebra. We've gone to geogebra.com and we're going to input our answer, that is that vector function. Now, in order to get a vector into GeoGebra, we're going to have to use lowercase letters. So I'm going to use vector, let's call it W, lowercase, to be representing, actually we could go ahead and call it R if we want to. R, lowercase r, is equal to open parens. And I'm going to input the vector function in my preferred form, which is to have all of the components added together. So 1 plus 2t was the x component of my final vector function. We have minus 4t was the y component, and then minus 3 plus 5t, and then close that parenthesis, and we see that we've got our line in three-dimensional space over here having been graphed in the GeoGebra platform. Now we want to verify that this is the correct line by seeing, does it pass through the given point that we were supposed to go through? So let's use, in order to get a point in GeoGebra, we need to use a capital letter. So I'm going to use capital P to indicate that I'm looking now at a point. Remember, lowercase letters with an open parens ordered triple gives me a vector. Capital letter gives me a point. So cap P, the order triple that I wanted to pass through was 1, 0, negative 3, and so we can see now that it actually plotted that point down here, and our line does pass through that point. So the other criteria that needed to be met was that it was in the direction of our direction vector, the given v. In order to get a vector, again, I'm going to do lowercase v, that gives me a vector, equals open parens, and the direction vector we had was 2, negative 4, 5. And you can see that with a direction vector put in like this, it automatically initiates it at the origin. In order to get it to be actually on the line, I would have to do all the algebra that we just did, right? So that would, our direction vector would be on the line if we have our vector function that we found a moment ago. We would have to find the vector function of this line to get that vector to slide over onto the line. But from here, basically what we can see here is that they are moving in the same direction, right? These two, the direction vector and the line are parallel to each other, right? So our line is in the direction of v, and it does pass through the given point.